the next speaker, please. The next speaker is Andrea Petrucci, who's going to talk about local Lorentz invariance violation and quantum mechanics.
So, hello everybody. I hope after talking about several practical things, we'll be talking about experimental and theoretical things. So the presentation is I'm trying to apply the violation laws of Lorentz invariance to quantum mechanics and see if we can get some information about the quantum effects. So basically, already in 1913, Rutherford spotted well, the first problem with quantum mechanics about quantum jump. And replying to a letter from Bohr, he said that it seems that the electron knows somehow where to jump and what frequency to do before jumping, but who tells the electron where to go and what frequency to do it. Several years later, basically with the EPR paradox, some physicists tried to fill this gap by and they talk about hidden variables. Of course, there were also other physicists who did not believe that these variables could be certain in quantum mechanics, and they tried to give some mathematical possibility. The last, as far as I know, the last spell with this discussion and these inequalities superseded these proof and possibility proof. Basically, he said that in those proofs, those proofs didn't give enough importance to the space-time and causality. So the space-time is something more prominent in this kind of discussions, the possibility proofs. And in his proof, he only requested the conditional locality, basically Lorentz and Stein locality. So the hidden variables are possible, but they are no local. I like reporting one of his sentences. Those paradoxes, so the quantum mechanical paradoxes, are simply disposed of by 1952's theory of Bohr, living as the question of Lorentz invariance. So one of my missions in life is to get people to see that if they want to talk about the problems of quantum mechanics, the real problems of quantum mechanics, they must be talking about Lorentz invariance. This is what I, with my colleagues, do. We violate local Lorentz invariance, and we see that the paradoxes of quantum mechanics apparently find their natural solution. So I will start talking about local Lorentz invariance, and I'll give some point of view about the theoretical, phenomenological, and experimental. So I will give some simple concepts about the form space-time. I'll talk about the forming cosmic space-time. I will show that the deformation is a local one, so it's a not global one. It's nothing to do with relativity, general relativity. I will show that there exists a maximum causal speed that can be superluminal. So basically, the correlation between cause and effect is extended. And I will show that the role of energy as the parameter to form the metric. Then I will apply this formalism to the propagation of an electromagnetic wave under cutoff in an undersized waveguide with superluminal velocity to determine several parameters of the DST theory. So we basically define the DST theory, which is a phenomenological theory, and I will apply it to superluminal experiment to determine the parameters. After doing this, I will show how it is possible to design a double-slit type experiment to study the effects of the known Lorentz invariant component of photons. and highlight the violation of the local Lorentz invariant from a geometrical point of view. So I'll show basically that local Lorentz invariance is not just superluminal velocity, but also has a very fundamental effect if we regard it, if we look at it from a geometrical point of view. And then I'll give some comments and of course results. So if we look at the special relativity from an axiomatic point of view, so basically we have these two postulates. So the usual isotropy of space and then homogeneity of space and time. And the second postulate is the principle of relativity, usual one. So we see that these two postulates give us a much larger freedom than the postulates by Einstein, because in Einstein postulates it says that C, basically C is the maximal causal speed for every phenomenon. But here we are free. So with these two postulates, basically for a correct formulation of special relativity, one is to specify the class of physical phenomena to which relativity applies. In fact, we have the Galilean relativity, which is applied to the mechanical phenomena, and we have Einstein relativity, which is applied to mechanical and electromagnetic phenomena. So basically, there is a change in the metric tensor when we move from the Galilean relativity to Einstein relativity. There's a change of the geometry. These two postulates imply the existence of an invariant real quantity, which has the dimension of a square of speed. So this speed, it doesn't say which speed. It doesn't say this is the speed of light. And in this sense, we are freer, as I said before. So this speed has to be experimentally determined in the class of phenomena and depends of the interaction rule of the physical phenomena. So there is a priori an invariant speed for each interaction, which is the maximal causal speed for each interaction. So if we want to include other physical phenomena in the class of phenomena to which relativity applies, we have to generalize the Minkowski tensor, as the Euclidean tensor was generalized to the Minkowski tensor. Now we have to generalize the Minkowski tensor to include other physical phenomena. And in doing this, we basically change the metric, and this generalization of the metric tensor is not a mere change of geometry. A generalized metric has a dynamic rule. It has an effective description of the interaction rule of the phenomenon. This is basically the Finzi principle. This is rule of Finzi, which says that each class of phenomena, namely each interaction, determines its own space down. This whole principle of solidarity is Italian, of course, and in Italian it would be principio di solidarietà. But you know, it was translated solidarity. It means basically that the interaction and the space down are solidly related to each other. They interact with each other solidly. So the mathematical tool to implement this principle of solidarity is the deformation of the Minkowski metric. So basically we start from the Minkowski metric tensor and we apply this very simple generalization. Basically, instead of a constant okay, no problem. Thanks. So we generalize this metric, Minkowski metric tensor, by putting some parameters on the diagonal. Of course, this is just an example. Of course, there could be other possible generalizations. This is what we did. For the sake of yeah.
pardon me just for going for the simple thing, but, well, we know the Minkowski limit is, or the Minkowski metric is a limit of a general metric, which may or may not be constant and may or may not necessarily be strictly diagonal. So if you're generalizing the metric, the Minkowski metric, wouldn't it be simpler just to say that you've got some sort of general metric instead of postulating a forming the Minkowski metric? What do you gain by trying to insist on the Minkowski aspect of it?
I'm not quite sure if I understood your question.
In other words,
Basically,
why not just use a general metric like you would use in general relativity?
This is we don't want to
Yeah, sorry.
Yeah.
Could we leave the questions till the end of the talk?
Oh, okay.
Yeah, you can answer the question at the end of the talk.
So for the sake of shortness, we indicate them like this in this one. Now, this generalized metric has a dynamical role, as I said. So these coefficients cannot be constant, of course, but they have to be functions of a set of observables. So here I show that if we in a very simple case, if we suppose that space is isotropic, so basically the coefficients of the four space coordinates are equal to b. And if we write the interval, the squared interval, we can find the maximal causal speed in the usual way. And in this case, we find that it's not equal to c, but it's equal to c multiplied by the ratio of these two coefficients. So depending on the values of these two coefficients, that in turn depend on this observable. This maximal causal speed could be higher than c, equal to c, or lower than c. So we have to find what these observables are. So the geometry of space-time is determined by some variables, so the determinant tensor. One might think that these variables could be, are you talking about hidden variables again? No, I'm not talking about hidden variables again, because we want these observables to be true observables. So basically what we decide to do is to use the energy. So the observable that determines the geometry of space-time, the local geometry of space-time, because it's always the local Lorentz invariance that is violated. It's not a general violation. What is this energy? The energy that we consider is indeed an observable, because we decided that it is the energy measured by the measuring instrument. So in this sense, this theory is a phenomenological theory, because we apply it to a specific, every experiment, to a specific experiment. So this sentence, which I highlighted, is quite important, because every measuring instrument carries out the actual measurement just by the electromagnetic interaction. So we basically say the electromagnetic interaction is our paradigm by which we interface ourselves with the rest of the world. Any measuring instrument that you can think, anyone, it works by the electric or electromagnetic interaction. So basically, whenever you do an experiment, whenever you receive you see a reading on your instrument, you are using this electromagnetic interaction that is in constant, so it's flat. And you are using this interaction to study a phenomenon which we think that could be flat, could live in a flat space-time, but could also live in a deformed space-time. So let's summarize what we have. We have a deforming Gaussian space-time with coordinates and the tensor. We have a deformed metric tensor, in which we specify now that the parameters depend on the energy. And then we have, so the DST theory is a phenomenological theory whose parameters have to be determined by applying it to physical phenomena. This is what we are going to do now. Why do we have an E0? We have an E0 there because the E0 is a threshold, is an energy threshold. There must exist an energy threshold because in everyday life we experiment that when the Gaussian tensor, the general relativity, is valid. So there must be a point beyond which these parameters have to become unitary again, 1 minus 1 minus 1 minus 1. So there must be an E0. So basically we have to determine this E0 by applying it to an experiment. We have to determine E0, we have to determine the function of these parameters. These two things. So okay, so we apply this theory to a superluminal experiment because we wanted to this theory is a theory to violate a local Lorentz invariance. So we take an experiment where the Lorentz invariance is violated in the sense that they measure the superluminal velocity. There are quite a few of these experiments. They're performed with microwaves that propagate in a waveguide. And this waveguide in the center has an undersized part. So in this undersized part, if you choose a frequency that is lower than the cutoff frequency, in this part you have an attenuated, exponentially attenuated propagation. Well, it's not a propagation, but you have the word about I can't remember the word anymore. So in this part, the wave doesn't propagate, but is attenuated. And what they find is that just in this part, the velocity is higher than c. So what we do, we write the D'Alembert operator in a deformed space-time. So basically, we make the scalar product by partial removal, and we use, instead of using the Minkowski tensor, we use the deformed Minkowski tensor, and we get this operator with the parameters. Of course, we resolve the wave equation. We resolve the wave equation, and we find the propagation vector that has this form. Usually, when you solve the wave equation using the Minkowski metric tensor, you have a 1 here. In this case, you have a ratio between the parameters, the time parameter and the space parameter. We have a b here, and we don't have b1, b2, b3, because to make it simple, and here we hypothesized that, we said, okay, let's b1, b2, and b3 equal to b. But this is just to simplify the discussion. So basically, in a flat Minkowski space-time, that's the word I was looking for, you have an evanescent wave, because the propagation vector is the square of the propagation vector is less than is negative. So the propagation vector is imaginary, and so you get an evanescent wave. In a deformed space-time, instead, you see that the propagation vector is a real vector. So the wave propagates, and that's it. Sorry, Minkowski spacetime of Einstein wave, and at the Lorentz spacetime, the wave continues its propagation. So this experiment that I showed before this was performed by Enders and Nims in Cologne in 1993, but there are several, hundreds and hundreds of these kind of experiments. So what they found in this experiment is that the time of propagation between the beginning and the end of the waveguide is independent of the length, this is L, the length of the undersized part. So they increase the length of the undersized part, and they find that the wave takes exactly the same time. So that means that its velocity increases as it gets attenuated by basically going through the undersized part. So this is the energy lost by the Lorentz wave in the undersized part. We hypothesized that this energy is the energy needed to deform the spacetime inside the barrier. I call it barrier. It's the undersized part of the waveguide. So basically, the energy that is lost by the Lorentz wave goes into the formation of spacetime. Okay. So, as I said, we have to determine the parameters of this theory. So we have to determine the B parameters, and we have to determine the function, their dependence on the energy, and we have to determine the E0, the threshold energy. From here, we have a relation between L, the length of the undersized waveguide, and the energy lost by the Lorentz wave that goes in deformation of spacetime. From here, instead, we have the maximum causal speed. Well, the speed of the wave inside the undersized waveguide, and this is measured in the experiment, and is linked to L. So we reverse this, and we obtain parameter B. So we get a P that depends on this velocity. This velocity depends on L, and also we have the energy that depends on L. So we have a connection between B and B and the energy. So we have the function. We can interpolate these data and obtain this diagram here. We have energy here. This energy is the energy that the wave lost inside the barrier, inside the undersized waveguide. And we have the B, the parameter B here. This is 1, so the parameter here is 1. And we have this interpolation of the data gives this this curve. This curve crosses one line, horizontal line, in 4.5 microeV. So basically, you have a deformation only when the energy is less than 4.5 microeV. So here, from 4.5 microeV down, you have a deformed spacetime with the parameter having this dependence on the energy. And if the energy is higher than the threshold energy, you go back to the Minkowski spacetime with the parameters equal to 1. There's also another experiment in which there is superluminal propagation. And this is the experiment performed by the National Research Council of Italy in 1993. They used two horn antennas, and they used microwave frequency again. And they noticed they performed this kind of experiment. They aligned the two antennas, and they measured the propagation time between these two antennas when they were aligned like this. And they saw that, yeah, well, it takes exactly an interval of time compatible with c, the velocity of light. Then they began to shift, to disalign the two antennas like this, yeah, and they measured again the propagation of the wave along S, yeah, this S, and they measured a superluminal propagation. So we applied basically the same formulas to this experiment, and but this experiment gives us the chance to make a hypothesis, because actually we want to show that we don't want to talk just about superluminality. Local Lorentz invariance violation it means superluminality. What we want to see is that local Lorentz invariance violation is the form space-time. So we want to measure the effect of the deformation. Because in doing this, in measuring the effect of the deformation, basically so measuring the energy stored in deformation, one would shed new light on several problems, like the question about reality, the existence of the Planck wave, or about the hidden variables, or about the lack of causality, beside that of locality and quantum jumps on the E-pure type experiment. So we would get quite a few information in doing this and measuring the effect of the deformed space-time. So basically, we considered this distance of the two node-aligned antennas. So when the antennas are aligned, the propagation takes place at the speed of light. When they're not aligned, we have superluminal propagation. This is the experiment. There's also this experiment. The hypothesis is that along S, beside the Lorentz invariant electromagnetic field, it exists and propagates the non-Lorentz invariance part of the field. That is, the formed space-time, according to the principle of solidarity. So basically we say, okay, the field propagating from here to here, but in this region there must be an effect of the formed space-time, because otherwise we wouldn't have superluminal propagation. So let's see if we can invent an experiment in which we can measure the effects of this deformation. So what sort of electromagnetic experiment can we design in order to measure the effect of the formed space-time? Do we have any indication to accomplish this task? We do have some indications and some clues. The first one is that we want to study the local Lorentz invariance breakdown from the point of view of space-time deformation. And this means that the experiment is to be designed according to the configuration of the antennas. Then we want to study the effects of the formed space-time on photon propagation. So the experiment has to be performed by two electromagnetic sources. The first emits the photons detected by some type of detector. So first source, some type of detector, these are the photons. And the second one has to generate a formed space-time that affects the propagation of photons emitted by the first source. Basically, this source emits its photons, but it also generates the deformation of space-time that somehow propagates along S, as we said, we hypothesized, and this deformed space-time affects the propagation of these other photons here. Then we have to perform, if we want to measure the effects of the formed space-time, we have to search them in a difference of measurements, because it's impossible to be aware of the deformation of a space-time or the curvature of a space-time. Okay, so basically we have to deform space-time, and we have to look for a difference, because Eddington did the same thing. When he wanted to measure the curvature of space-time around the sun, measuring the position of the star and the distant star, he made two measurements, and then subtracted the two measurements, and he got an angle. So we have to do basically the same thing. Then we have a relationship of time to space-time in terms of the different space. So we have to design something like a double-slit target experiment. Unfortunately, we have the critical points that we have no indication on the time evolution of lower Lorentz invariance. So we have to see how to deal with this problem. So this is the experimental setup. Basically. This is a box. This is about 17 centimeters. This is about 10, and the thickness will wear about 7, 8 centimeters. It's a closed box divided into several rooms by panels. There are 3 slits, well, one here, and one here, but here we have the detector slit right on the slit. They're not actually slits because we call them apertures. Maybe it's better because they are 0.5 centimeters in diameter. There are two LEDs, 2 infrared LEDs, and 3 detectors. That could be photodiodes or photo transistors. So the detectors see. Oh, by the way, the panels were completely painted. Well, they don't reflect. These 2 sources are infrared sources, and we made so that the panels would not reflect the infrared frequency used. So the detector C detects the photons from the source S2. The detector B controls the dark. Basically controls that through aperture F2, no photon from the source S2 pass. And the detector A is the principal detector where we perform the actual measurement. So I'm going to show you that this line is this line. So basically this distance, this triangle here is this triangle here. So we design according to this experiment, according to the hypothesis. The setup was designed so that the detector A must not be affected by the lighting condition of the source S2. So whether the source S2 is on or is off, the detector C should not be aware of this, of the lighting condition of this source. Of course, we made a conjecture as well because the threshold energy, we found the threshold energy, the 4.5 microeV in a microwave range, and we're using the near infrared range. So we hypothesized that this threshold energy is also valid in the infrared range. The effect is to be certain in difference to lighting conditions. So the first measurement, the first group of measurement on detector A is when the source S1 is on, source 2 is off. On, off. And we collect the measurements, the energy detected by detector A in this condition. The second type of lighting condition is when we have S1 on, S2 on. So both sources are on. And we collect other data from the detector. The third measurement is just the same as the second one. So we have a blank difference, which is basically the difference between on and on. So we expect this difference is equal to or is compatible to 0. And then we have the difference carrying the physical information that we're looking for. That is the difference between the first type of measurement with S1 on and S2 off minus S1 on, S2 on. But as to what I said before, that the detector A should not be affected by the lighting condition of the source S2, these difference should be compatible with 0 because it doesn't matter if this is off or this is on. So, well, the first experiment, we had three experiments. I think that I haven't got much time, so I skipped. I'll go quickly as this we could again. So I skipped this. I will the second one. So the first one was with the photodiodes. The second one, the phototransistors, and we go to the third one. So the third experiment again with photodiodes. We So we performed the measurement as I explained, and we have the difference carrying the physical information on of minus on, and then blank difference. So this is the blank differences, okay? So it's data compatible with 0. So it's on, minus on. Same type of lighting condition. As to the difference carrying the signal information, they are non-compatible with 0. The difference carrying the physical information are when the first source is on and the second is off, and when the two sources are on. So it's the difference between these two conditions. We expect that they are compatible with 0. Unfortunately, they're not. We obtain this result here. Of course, some of these differences were compatible with 0, but we discarded them. So the same thing, but these are compatible with this band is the band of compatibility with 0. So we discarded these differences. So let's give some remarks on the sign of the differences. The sign of the differences is positive. So it means that this is larger than this. But this is strange because in this case there are more photons in the box because two sources are on. So this is an interesting result. This kind of destructive interference, we could call it, cannot be accounted in terms of destructive interference because the sources are LEDs, so they're incoherent sources. They can't be so. It's a constant. They're all compatible with they're all higher than 0. So then the difference is the mean is 2.3 micro eV, micro eV. So it's less than 4.5 micro eV. So it's less than the threshold energy, and so we are in the below the threshold, and hence in the non-Lorentzian region. And then this value is 2.3, and I didn't show it, but in the first and in the second experiment we obtained this we obtained a value that is compatible with 2.3. So let's go to interpretations. The interpretation is that the results are not accountable in terms of standard quantum mechanics because the detector C destroys the photons here, and the detector B controls that there's always dark, so there are no photons go through here. Vice versa, the results are strongly in favor to us in favor of Bohmian mechanics or pilot wave. In other words, the pilot wave of these photons goes through, it propagates to regions of space experimentally forbidden to the photons of the sources too. So pilot wave moves through the aperture of 2, it reaches this area, it interacts with these photons, with the pilot wave of these photons, and steers the photons of the sources too. So what we state is that the pilot wave is only a synoptic concept, and that together with the hidden variables can be replaced by the space-time deformation. And we say that from these experiments we see that the physical entity photon is a complex system. Most of its energy is concentrated in the tiny extent that we know. It's complying with Lorentz invariance, with electrodynamics, with relativity, and with cosmic space-time. But the rest of the energy is used to deform space-time surrounding it, violating Lorentz invariance and having real, non-local, and superluminal features. So basically, we've seen that the local Lorentz invariance violation is wide implication. It is superluminality, okay, but more importantly, it means that space-time takes a dynamical, active part in the physical phenomenon by its deformed geometry. The deformation of space-time and its superluminal velocity can account for the apparent lack of causality in quantum mechanical description of quantum phenomena, and for the non-locality, providing a concrete physical explanation to the non-local character of quantum entanglement and physical reality to inner variables. So the results of this experiment allow us to say that the effects were brought about by the foreign space-time, and that the steering of the photons by the foreign space-time is associated to a measurable energy, and this energy difference is lower than the energy threshold, as I showed, and therefore we are in the non-Lorentzian region of the electromagnetic interaction. Okay. Thank you for your time.
Time for only one quick question. Ludwig.
I would like to ask you a question, but before I have introduced some ideas. When I wrote my Habilitationsschrift, I had to read all the papers written by Einstein and also non-published papers, because I received such a permission. And Einstein made a clear distinction between reference spaces, Bezugsräume, and the so-called space as such, the Raum als solche, or the space as whole, das Raum als Ganze. According to Einstein, there exists only one physical space, one and only, one physical time, one and only, one space-time, one and only. But all other spaces are reference spaces. And these reference spaces he called sometimes box time. When we have many cars, every car has its own box space. And I ask you the question, you are talking about these box spaces, because the space as such, according to Einstein, is not divided in part, it's not composed of points. We cannot use the notion of motion or rest with respect to this space as such. Also with the time is not divided in time intervals, not composed of moments. We cannot say that time is flowing or not flowing. And in the four-dimensional description, where is time and space together, Einstein said that the space-time as such is not composed of work lines, because a point corresponds to a work line, and not of instantaneous spaces. So also, but you are talking about the deformation of this box spaces connected with this concrete particle or concrete atomic system. Is this true? I have good understood, because the box spaces are infinite. They move with respect one to other.
I think so. I think in this kind of presentation, I speak about this the box space-time, space-time in the box.
The box space is deformed.
And the box space is deformed. Yeah, I think so.
We'll have to, press on to the next speaker.